Okay, so first, anybody have any homework questions? Read B. Okay. I don't have that with me. Do you have it there? It's basically like we have a. Okay, 3. Um, uh, so there's a vector A, and it makes an angle of 20 degrees with the horizontal. And then there's a vector B that makes an angle of 15 degrees with the vertical. Um, and this one has a length of, the one on the left has a length of 4.5, and the one on the right has a length of 3.8. And the lettering starts at C. That shouldn't be. First, in the first part, I'll call it A. In this coordinate system, the one that we're used to, calculate A plus B. And so the first thing you have to do is come up with the components of each of these two vectors. So to do that, put the tail of each vector at the origin. So there's that one with a length of 4.5. And here's this one with a length of 3.8. So the vector A is equal to 4.5 times, you can calculate that as the cosine and sine of, since you go counterclockwise from the positive x-axis, this is cosine and sine of 20 degrees. No. So this is it right here, right? So if you are gonna, so you always start at the x-axis, okay, the positive x-axis. And so if you go counterclockwise, you go positive 20. If you go clockwise, which not many people would do that, but it's fine. You'd have to go clockwise 360 minus 20, so it would be negative 340. Okay, and what do you get for numbers there? Anybody have that? Yeah, for 4.23, 1.54. Okay, so that's the vector A. And then the vector B is 3.8 times, this one you can do as 270 plus 15. So 285. Or you can do it as negative 75. Or you could do it, just use SOHCAHTOA and say, you know that you're going to have a positive x component and a negative y component. And then just, this angle is 15. So this is going to be, this horizontal component here, the positive one, is going to be 3.8 times the sine of 15 degrees. And the vertical component, it's going to be negative, and that's going to be 3.8 times the cosine of 15 degrees. So any one of those three ways works fine. What do you get for that? Anybody? Yeah. You always start at the x-axis and go to the vector. So you start here and then you just go 20 and you're at the vector. Did you get an answer for 3.8 times the 3.8 length one for the vector components for B?
Oh, yeah, I got 0.9.
9, 8, okay. Okay. And so then A plus B is just adding those components. And you get 5.21. Okay, that one wasn't so bad. How about this one? Thank you. Draw it. Mm-hmm. Yep. You should be able to do both of those. And if you want to see what the resultant vector looks like, it's just a matter of plotting that point. So, go up 5.21, down 2.13, and then the vector has its tail at the origin and its head at that spot. So it looks something like that. And then part B. So now we have a new coordinate system. The x-axis is there. The y-axis is here. The vectors don't change. So that's still A. And that's still B. But you're going to get different angles now. So that's vector A. Start at the x-axis, positive x-axis, go counterclockwise until you get here. So that would be, in this case, 90, 180, 270 plus 20, so 290. Or you could go negative 70. So 4.5 times cosine and sine of 290. And what do you get for that? Okay. Oh yeah, makes sense. And then for B, that's 3.8 times 180 plus 15, so cosine and sine of 195.
Wait, how's it like 195? I got like, I thought I got like negative 1.165 degrees because I started from
160. You can do negative 165 too.
Because I start from that vector and I go all the way through this.
So you went clockwise,
yeah.
And so you went 180 minus 15, so 165, that's right. Or you can go counterclockwise, and then it's positive 180 plus 15.
Oh, okay.
They give you the same answer. And I guess that's going to give you negative 3.67, no, negative 0.98. And then it asks you for, 2 times A minus 3 times B, which is just 2 times 1.54, negative 4.23, minus 3 times negative 3.67, negative 0.98. Any other homework questions? Sure. That's on the other sheet. Anyone have the? Okay, seven. That's French for seven. That's Spanish. Yeah, multilingual. Consider the vector equation. So Pf is equal to P sub 0 plus V0 Tf plus 1/2 A Tf squared. Well, it doesn't really change the problem, but I'm going to get these F's out of here. So now it sort of matches the form that we used in one-dimensional kinematics. And now we're going to rewrite this equation in terms of the components. So P, I'm going to rewrite as Px, Py. And that's equal to P0x, P0y plus V0x, V0y times T plus 1/2 times AX, AY times T squared. And now use the rules of vector math to rewrite this into two separate equations. So we're going to have one equation that's all the x components and one equation that's all the y components. So first, I'm going to just use the rules of multiplying vectors by scalars to come up with a vector equation where everything's pulled into the components. So we have Px, Py is equal to P0x, P0y plus, if we multiply this V0x, V0y vector by the scalar t, what's the x component of what we get? That's right. And the y component is V0yt. And then we're going to do the same thing twice with the 1/2 and with the t squared. And so that gives us 1/2 ax t squared for the x component and 1/2 ay t squared for the y component. And now I'm just going to break it into two separate equations. The x equation says px is equal to p 0x plus v0x t plus 1/2 ax t squared. And the y equation says py is equal to p0y plus v0y times t plus 1/2 ay t squared. This is, so you recognize that equation. It looks almost exactly like the position equation for one-dimensional kinematics for motion with constant acceleration. In two-dimensional kinematics, you have two separate equations, the ones that depend on the x components and the ones that depend on the y components. And those two equations are completely independent of each other. Notice that there are no y components in the x equation, no x components in the y equation. And so something, I mean, I'm going to emphasize this, get it in your notes later on, but just coming down the pipe is this thing where none of what happens in the y direction is going to affect what happens in the x direction. None of what happens in the x direction is going to affect what happens in the y direction. Those two things are independent of each other. Any questions about that problem? How about any other problems? Question? Okay. So last time we started talking about yeah, it's at the end. Yeah. So last time we talked about the position vector. And you can think of the position vector as just the coordinates of the object in whatever coordinate system you're using. So now we have to talk about the velocity vector and the acceleration vector. So the velocity vector as a function of time is just equal to the time derivative of the position vector, which you can, this means exactly the same thing, the position vector dot. And mechanically, like, how do you go about taking the time derivative of the position vector? Well, if you know the position function, x and y components, then you just take the time derivatives of the individual components, and those are the components of the velocity vector. I'll do an example of that at the end. The velocity vector you can think of as having two properties. Well, all vectors have two properties. They have a magnitude and a direction. The two properties of the velocity vector, like every other vector, are its magnitude and its direction. But its magnitude means something. Its magnitude is the speed of the object. And its direction is the direction of the object's motion. And that's tangent to its path. Okay, so for example, let's say you have a little mass on a string and it's swinging around a circular path. Let's say it's going this way. Then the path is the dotted line. And so the direction of the velocity vector is tangent to that path. and the magnitude at that instant is the speed. One thing I want you to keep in mind, and this is going to be an important thing for understanding this stuff the whole semester, is the velocity vector is tangent to the object's path in the physical world. So that's not a position versus time curve. Okay, so sometimes position versus time curves can look sort of similar to object paths, especially like if you're dealing with something in projectile motion. It can be sort of confusing which one you're looking at. You need to be clear with yourself about which one you're looking at, because the velocity is tangent to the actual path. Like if you, like by the actual path, I'm saying if you do this motion with a light stick or whatever, like a glowing object, and do a time-lapse picture of it, you're looking at the actual path it takes. You're not looking at a mathematical representation of it. Okay, so let's say that the position vector as a function of time is equal to 10 times the cosine of the quantity 2t, and then the y component is 5t squared. That's the velocity vector as a function of time. And then actually, once we do that, let's figure out what's the velocity vector at the instant when time is equal to 1. Okay, so the velocity is the time derivative of the position. So that's equal to negative 20 sine 2t. Did I do that right? And then the y component is 10t. So that's the velocity as a function of time. Just take the individual derivatives of the components. And then second, we want to know what's the velocity when time is equal to 1. So just plug 1 in for these two things in the velocity function, and you get that the velocity when time is equal to 1 is negative 20 times the sine of 2 and 10. Is that 2 in degrees or radians? Pretty even split. Anytime you're taking a derivative of a trig function, it has to be in radians. Otherwise, that's true in every class. For the chain rule to work, that has to be the case. Yes? Before, for the chain to take the derivative, or the second one? Yeah, all we're doing is the time that we're looking at is 1 second, so I just plug 1 into my two functions. So I get negative 20 times the sine of 2 times 1 is just sine of 2. And I plugged it in here, and we just get 10. Any other questions about that? Um, and so that's just a mathematical thing. We just took the derivative. But if we went through and figured out what the path of this object looked like, and then at the instant, and then on that path, located the place where time is equal to 1, and then drew that vector for v, we would see that that vector is tangent to the path at that instant. Cool. Yes? The v? So yeah, this is saying that, yeah, that's actually pretty weird. Oh no, this is the function. Okay, so this is saying uh, whatever the path looks like, and it's some kind of weird sinusoidal. If you locate the place on the path associated with that time, okay, and then plug that time value into this, it will give you back a vector that its magnitude is the speed of the object at that instant, and its direction is tangent to the path at that point. And what are the units of velocity vector? Yeah, in SI units, it's meters per second. It has to be length per time, whatever units you're using. Okay, and now the acceleration vector. The acceleration vector as a function of time is time derivative of the velocity vector as a function of time. That means that it's the second derivative, the position vector, as a function of time. Since acceleration measures how quickly the velocity is changing, zero acceleration and constant velocity mean the exact same thing. You can think of that as two different ways to say the same thing in a problem. Okay, that's also true if you think about the fact that velocity is the time derivative. It's measuring how quickly the position is changing. Zero velocity is saying the same thing as constant position. Okay. And now, as far as interpreting the acceleration, that was what we did in lab on Friday. So I'm going to say some of that stuff again. In 1D, non-zero acceleration means, what does it mean in 1D? So in 2D, it means the velocity is changing too, but the speed is changing. Okay, all it can do is speed up and slow down. In 2D, though, there's two different ways the velocity vector can change because a vector has two properties. You can change its magnitude, that's changing the speed, or you can change its direction. So in 2D, non-zero acceleration means the speed is changing. That can still happen. Or the direction is changing. In other words, the object is turning. There's no such thing as turning in 1D. To get an intuitive picture of acceleration in 2 dimensions, 2D, we're going to go through these steps. And this is basically what we were doing the whole time in lab on Friday. So what's the first one? Draw the path. Is that what you said? If not, okay, good. I always do that where, like, if someone says something and I don't hear them very clearly, I just assume they said the right thing, so I feel better about myself. So first thing is sketch the path. What's the second step? Draw velocity vector. So draw the velocity vector tangent to the path. Third is draw the part of the acceleration that's parallel to the velocity. And the way you do that is if the speed is increasing, then a parallel is in the same direction as the velocity. And if the speed is decreasing, a parallel is the opposite direction, v. And then fourth, draw, well, if you've already drawn all the acceleration that's parallel to something, anything, in this case v, then the only other part of the vector has to be perpendicular to it. And so now we're going to draw a perpendicular. And that's going to be in the direction of the turn. So which way is the object turning? And then the last step, the total acceleration is just the sum of these two. If you only have one or the other, like if the object is speeding up but it's not turning, then you know that the acceleration is in the same direction as a parallel. If it's not speeding up or slowing down, but it is turning, then you know the acceleration is all perpendicular to the velocity. Okay? If both of them are non-zero, then you can only, through this kind of analysis, you can only figure out within 90 degrees. Okay? So let me draw an example. This is just like the stuff that you did in lab on Friday. Let's say an object's moving along this path. And let's say we're interested in what's happening at this instant here. And let's say the object is slowing down this whole way. Okay, is this position versus time graph or a path in the physical world? This is the path. So the first step is to draw, like, trace the motion of the object through space. Then after that, okay, we have to know which direction it's going along that path. The velocity vector is tangent to the path in the direction of motion. It's slowing down, so the parallel part of acceleration is opposite that. Stay on the path, you have to turn this way. Like if there was a steering wheel inside there, you'd have to be steering this way. And so the perpendicular part of the acceleration is this. And so the total acceleration is somewhere in that 90-degree range. Any questions about that?